let me just get. Yeah, you can see that marker on the screen.
Yes, yes, I can see your markings.
Isn't it artistic? Yeah, you can see that marker on the screen.
Yes, 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 I can see your markings.
Isn't it artistic? Yeah, you can see that marker on the screen. Yeah, this is the live, because it's live streaming, it's we're getting background noise. Okay, you can see all that fine, Helen, and hear me well?
Yes, I can see you.
Excellent. Okay. Yeah, so basically ready. Now, when you go, are we live streaming at the moment?
Yes, yes.
Oh, excellent. Okay. Okay, I'm ready. How have things been going over there in the industry?
Pretty busy.
Yeah, same here. It's so wonderful to see a lot of commercial businesses seem to be, we're getting involved, getting things going. I'm involved with a number of quantum application developments, which is very exciting.
Yeah, and we've been having a lot of great events.
Yes, well, you always have. I remember going to one of your events, I don't know, 2.5 years ago. When did you actually start?
About 2019.
Yes, yes, excellent. So I'm just putting a quick message in the chat.
David, you asked your question. How is winter coming in Australia?
Yes, well, I'm in the west of Australia, and the west of Australia, so I'm in Perth. So it's a long, long way from Eastern Australia. So we're just coming out of our summer, which was horrendously hot. So yeah, but it's still like it's a lovely day today. I think it's about 24, 25 degrees already, and it's only 7:15 in the morning. So yeah, we're blessed with a good climate here. I'm actually English. I don't know whether you can tell, but I've lived here over 30 years.
Yeah, I thought you didn't sound like an Aussie. You sound more like like an Englishman. So
yeah, exactly right. But I mean, look, I have been here over 35 years or something like that, and it's a wonderful, wonderful country, and we're doing very well in the quantum, arena. Not far from where I am, we have the fastest supercomputer in the Southern Hemisphere, and we're involved with, and it's really experimental. It's leading edge. We're actually hooking up a quantum computer to the supercomputer, the HPC, and there's not that many people doing that around the world, so it's good.
yeah, I was looking at a couple of good researchers from Australia, and I think IBM and also Microsoft topological quantum.
Yes.
Now that research is now based in Australia. So I think they're doing quite well, actually.
Yeah, they are in New South Wales. Yes, they definitely are. I know the chap, oh my God, I can't remember his name now. The chap who was from Google, he went to New South Wales, and they were looking at the topological qubit there. So, and they do a lot of silicon spin qubits, so it's interesting. And Microsoft just had a bit of a breakthrough not so long ago with the topological.
That's correct. Yes, that was a big breakthrough because they almost gave up on the idea, and then now it's back. That
Absolutely. It is wonderful. Well said. Sorry, may I ask who I'm speaking to? Because sorry, what is your name?
My name is Sam, and I'm based in the UK. I'm at the Oxford University, actually. So
excellent.
So, which is why I figured this out. The Microsoft one is pretty fantastic because those qubits have a by default advantage of error correction.
Oh yes,
and they're wonderful. So yeah.
Yeah, the Majorana fermion, basically.
Yep.
Yeah. So, and as you say, they gave up on it, Sam, didn't they? Only about a year ago, it all went wrong. But that's the thing about this industry. Obviously, it's a nascent industry, and we're starting off, but we still don't know what's going to be the best technology. The reality is, we just have to keep a quantum particle in superposition. So whatever technology can do that for with as least noise and interference is going to get ahead. And as you quite rightly say, Sam, the topological and the Majorana fermion is going to, I've always thought it's going to lag behind for years and years, and then one afternoon it's going to zoom straight to the top.
I think IonQ is also doing something fantastic, and that's reflected in its share price as well. They're also investing in a quantum battery, which is that's something of their special thing. There's a professor from South Korea. He's on the board of directors and a top researcher.
Yes.
So So that's an interesting play as well. We'll see what happens there. They've come out with a new gate as well.
Okay.
Again, I haven't had the chance to read all through it, but they're doing quite well.
Yes, they are. I know Denise Ruffner there very well, who was the vice president of marketing or whatever. She's moved on to atom computing, but yeah, IonQ, I mean, trapped ion is obviously one of the leading technologies. So yeah, that's really interesting, Sam. Sam, I'd love to keep in touch with you if that's possible. Maybe if you could subscribe to my channel or whatever, or I was just thinking, I haven't got my email anywhere here on the slides, but I'd certainly like to keep in touch with what's happening over there in the motherland.
This is a funny one. I like that. By the way, whereabouts in England do you come from?
I'm from the capital of England, Liverpool.
Oh, you're from London, are you?
No, I'm from Liverpool. I always tease people like that.
Yeah, because you sound more like, up north. So that's why I was thinking, right.
Yeah,
okay, fair enough.
Yeah, no, I always say to, especially English people, when I meet them here, I always say, yeah, I'm from the capital of England, Liverpool. I mean, wherever the Beatles are from, that has to be the capital of the country. That's only fair. Yeah, when I first came, sorry?
Go on.
Yeah, I left England many years ago, and I lived in Bermuda for a number of years in banking, and then came out here, and it's fantastic. And what about yourself, Sam? Were you born in the UK?
Yeah, I was born and brought up in the UK. I lived in London. I did my undergrad at Newcastle, and then I went to Oxford. And, it's kind of like on and off. I lived in some other countries as well. I lived in Japan, but, I haven't perhaps not as extensively traveled as you are. But
oh, no, I'm not particularly traveled, but yeah.
I got lots of friends in Australia from my university, as well as, work colleagues and stuff. So, yeah.
Excellent.
In Perth.
Who do you know in Perth? Because
there's one of my friends. So I think when I was in my first year at the college, there was this mature student. His name is Patrick, and I recently found him on LinkedIn, and he's in Perth. He's some director or something, and he doesn't respond. But he's quite a big Joe now, I suppose.
Oh, excellent! Oh, that's all good.
It's past my bedtime though. It's 12:30 over here. So.
Oh, is it really? Oh, well, you're allowed to leave halfway through then.
Now I'm writing a paper. You see, I'm writing a paper on the quantum security, and and therefore I come to these not only to gain knowledge, but if there's something really exciting happening that I can pick up and go and look at that. And now I'm at a point where I need to make some submissions pretty soon. So I quite enjoy these meetings. I come here quite often, but then it's becoming now a point where a lot of things are catching up because the world is opening up, and so everything's moving really fast.
Yes, indeed. And I'm a bit being in WA. Lots of presentation are on at terrible hours for me, like 2 or 3 in the morning, and it makes it very difficult. But there's an awful lot happening at the moment. Are you concentrating on QKD, or are you doing many different things?
So everybody kind of obviously talk about QKD, and QKD is the only practical technology that actually is working, pretty well known and everything. But obviously in my paper, I do mention QKD, go through it a bit, but then I tear apart every single primitive of security that we know. whether it's
Yeah.
blockchain, whether it's hashing, whether it's symmetric encryption, whether it's asymmetric encryption, every single bit of that. And then I twist it
Wow.
around on its head. And then I say that, hang on a minute, it's all not all that bad, because we can turn this around and now try to get value out of it and do some threat modeling and work out blah, blah, blah. And,
Yeah.
try to reason on the base of that.
Oh, that's really interesting.
Whether it's hashing, whether it's symmetric encryption, whether it's asymmetric encryption, every single bit of that. And then I twist it around on its head. What? And then why is it being recorded? Hang on a minute. It's not all that bad, because we can turn this around and now try to get value out of it and do some threat modeling and work out blah, blah, blah. And, try to reason on the base of that.
And yeah, someone earlier said
and then I twist it around. And then why is it being recorded? Hang on a minute. It's not all that bad, because we can turn this around and now try to get value out of it and do some threat modeling and work out blah, blah, blah. And,
yeah, someone.
What's going on?
Someone mentioned earlier, say, I think it's a Zoom corner. You mentioned INQ has someone from Korea. Is her name Patty Lee?
I don't know. I can check that for you if you want. Give me a second.
Yeah, please.
Yeah, Helen, we're getting a bit of feedback from the live stream, I'm pretty sure it is.
I'll be watching the live stream.
Oh, is that what was that? Okay, I see.
Patty Lee?
Yeah, is that right?
I don't know. I can check that for you if you want. Give me a second.
Yes, please. Yes, please.
Yeah, Helen, we're getting a bit of feedback from the live stream, I'm pretty sure it is.
Yes, David Liu, is this real? The world's first room temperature quantum computer is in the final stage of the development and is set to install at the Palsy Supercomputing Center in Perth.
Yes, at Palsy. It's a quantum brilliance diamond. So it's a nitrogen vacancy technology. And yes, it's being installed at the moment, and it is a room temperature diamond quantum computer. And they've also got the SpinQ one there at the university, SpinQ from China. I think that's room, I'm pretty sure that's room temperature as well.
So somebody just now asked me about the person from South Korea. The name of the person is Jung-sang Kim, and he's the co-founder and the chief technology officer, I think.
Okay, it's a he, not a she.
It's a he, yes.
Okay. We are talking about two different people. Okay, thank you. Eamonn, Eamonn, I hope I say your name correctly.
Oh yeah, it's Eamonn.
Eamonn, okay, thank you, Eamonn. Earlier you mentioned, just now mentioned some computer with diamond. Is that
yes?
Is that is a non-charged molecule, right? Or is a charged molecule?
Yeah, it's. Have you heard of NV-centered, nitrogen vacancy centered quantum computers? Yeah, where they basically they create a vacancy where they can then manipulate the remaining electron. But there's quite a lot on there. It's a company called Quantum Brilliance, who have received significant funding.
Okay.
Yeah.
They were using electron, or they were using nitrogen
Vacancy centered, yeah. And
So
NVC
essentially what that it is, it's a point defect in a diamond lattice.
Yes,
And
yes.
and basically nitrogen itself, I can't remember the atomic number of nitrogen. By default, it has this nearest neighbor pair of a nitrogen atom, which basically substitute for a carbon atom and creates a lattice vacancy. And that's what it is.
Okay,
Yes.
I'm just trying to figure out whether, why they just need it at a room temperature. This particular quantum computer just, that does not need a super cold.
Yeah, I mean, like I mentioned before, it's all about keeping the quantum particle, whichever it may be, in superposition, so isolated. So there are different ways of doing that. And as Sam says, the natural lattice structure of a diamond affords that ability to keep the quantum particle isolated. Okay. By the way, did I see Anna come in?
The
and
two
by the way,
arrived. The two
by the
moderators
way,
arrived.
The person I mentioned, Jung Sang Kim, is a professor at Duke University, just in case you want to check him out.
Okay, thank you. Yeah, I see there's a lady, her name is Anna. It's among us. I think, if this person is Eamonn asking.
Yes, thank you. Anna's a very good friend of mine, and I hope you're there, Anna, and we need to talk soon.
Yeah, I'm here.
Oh, hi, Anna. How you doing?
I'm good. How are you?
Excellent. I'm looking forward to the presentation. I don't normally start at 7:30 in the morning, but I have to do so for you American people. Actually, speaking of which, how are we going, Helen?
Good. The moderator arrived. Henning, please introduce our event and yourself.
Sorry, are you talking to me?
Henning arrived. The moderator of tonight, he arrived.
Hi, yeah. So sorry for being a little bit late. So this event here is dedicated to one of the more revealing and most peculiar aspects of quantum computation, quantum information, in that we cannot copy quantum information like you're used to with classical information. And really, if you think about it, everything that we do with classical computers kind of evolves around the ability to be able to write and to replicate it at will. But in the quantum information space, we can't do that. It's known as the non-cloning theorem. But what we can do is we can teleport. And it's most peculiar really in that that teleportation essentially takes the entire state that we have and reconstructs it somewhere else, which gave it the name, obviously, teleportation. It's really kind of like what you've seen in Star Trek, sci-fi at some point. You get the whole thing, and you leave nothing left of where you originated. But it's not the thing itself that gets transported. It's really just the quantum information. But that is, in essence, the thing itself, because what defines what we actually see and what we actually experience is nothing but the quantum state. According to physics, really, this is all there is to a thing to make it identifiable. Anyhow, so yeah, I'm very excited to be here and hear this talk tonight. And without further ado, let's head over to Eamonn. And you're based in Australia, right? So it's really early for you, if I'm not mistaken.
Yes.
So thank you.
Pleasure, Henning, and thank you for that wonderful introduction, because you've hit the nail on the head on a number of issues. quantum teleportation is obviously the sexy part of quantum physics and quantum computing, if you like. It is absolutely unbelievable what has already been achieved. I mean, I think a lot of you will already know that I think it was 2016 or something like that, 2019, the Chinese quantum teleported a photon from a laboratory in Tibet to an orbiting spacecraft, the Messias. So I do a bit of teaching in quantum computing, and I like, teaching it to young people, teenagers, 14 to 17. And I always start off with quantum teleportation because it's just unbelievable. You can put a little speck of dust on your hand and boom, that speck of dust is 150,000 miles away. Although I know it's not a speck of dust. And as Henning quite rightly says, all that's being, which I say in my presentation, all that's being done is, well, not all that's being done because it's unbelievable, but it is the quantum information that is amazingly transferred through the mystical wonders of quantum entanglement. But let's get into that. We have an awful lot to get through. The actual presentation is sort of aimed at showing how the theory, as the name suggests, the theory of quantum teleportation is so simplistic. It's unbelievable that just by knowing a few gates, a little bit about the Bell state, we can actually understand how it's all done. And I think a lot of people who are new to quantum computing, they think, oh, quantum teleportation, we'll put that to one side, too difficult. But so the purpose of this presentation is really to say how extraordinarily simplistic it is, because quantum entanglement's doing all the hard work. But we do go into, in fact, what's on the screen now. So let me read out the agenda. I'm going to begin by talking about what do we mean by quantum teleportation. As Henning quite rightly says, it is the quantum information that's being transferred. And then I'll go into an elevator explanation where we can explain the whole process in just a few paragraphs. And that's, again, on the theme of this is, in theory, wonderful and easy to understand. Then we can go into it a bit deeper. And
you're not sharing your screen.
Oh, the sheets. Oh, I should. Oh, I'm glad someone said that. I can't.
Yeah, sorry. I thought you were still in the introduction phase.
Oh, no,
yeah,
that's it.
We see you, but we don't see your screen indeed.
Oh, my God.
Can I guide you quickly? Just click on your share screen and pick up the...
No, I'm trying to. It's not allowing me.
Bottom, middle, bottom, and then pick
No,
up
no,
the...
I know where it is. It's not allowing me to access that. Oh, my Lord. Okay, so here we go. I don't know why that happened.
Yeah, we can see it now.
Excellent. Just move that out of the way. Slideshow. Okay, can you see that?
We can just see you're trying to share good morning and recent pin shared with me, not the actual slide yet, Dr. Eamonn.
It says here that I'm screen sharing.
Yeah, I think we can see your screen, but what we see is a list of your PowerPoints, not the PowerPoint itself.
Yeah. I think easiest is if you share the entire desktop, because we'll be only seeing your slides.
Yeah, okay.
Yeah, that would be fastest.
I do apologize for this.
That looks promising.
Perfect. Now
I see the banner, yeah.
Yeah.
we're good now.
Yeah, so, right. Okay. All right, let's start again. So look, here's the agenda. I'm going to be talking about what we mean by quantum teleportation, basically what it isn't, and what is happening, and then the elevator explanation, which is just a very quick overview of the process and how simplistic it is and how amazing it is because of quantum entanglements. It allows us to do it very easily. But then we'll go into the background. So what's the quantum background knowledge you need to have? And we talk, so I'm going to go into creation of a Bell state, and then the rotational invariance of Bell states, and complex amplitudes and basic quantum gates. And that's just so that we can see not only how simple it is, but we can discuss what's going on. So then I go over the process, and then we can have a discussion about why it works and how it works. And it's so fantastic, as Henning was saying. So what do we mean? Well, by the way, I'm just checking, can everybody still see the screen?
Yes, we can.
Yeah, excellent. Okay, so what quantum teleportation isn't? It isn't moving a particle from one location to another by going through a wormhole in the fabric of warped space-time. Now, that may or may not be possible, as we're finding out in other things. But we're not talking about wormholes or going physically through space and time. It's also not the beam me up Scotty Star Trek type thing, where every atom of the object is disassembled and then reassembled. And as I say, I've given this presentation or something very close to young people, and they stopped me and said, "Oh, not beam me up, Scotty. You're talking about what happens in Willy Wonka and the Chocolate Factory." So I have to update the presentation to include that. And we certainly aren't talking about whole human beings being teleported. That may happen one day, never say never, but we're a million miles away from there. What is it then? It is the transfer of the quantum information of a quantum particle in superposition. So it's somehow forgive me for laboring the point, but it's somehow in a very simple process conveys these extremely complex bits of information. And we really don't know how it's doing it. And we'll have a good talk about that later. Nothing moves, no one's moving, no cats are being heard. The complex amplitudes of psi remain unknown. So we teleport them, but we don't know them from where we teleported, we don't know them, and where they're received. We don't know the complex amplitudes of psi. The original is collapsed, as Henning said, the no cloning theorem. And again, as I just mentioned, a photon was teleported from a laboratory in Tibet to an orbiting spacecraft, the Messias. So it's being done, it's there. When I talk to the young people or people new to quantum computing, I say, talk about teleporting a quantum particle from Earth to an orbiting spaceship. When do you think we'll do it? In 30 years, in 50 years, 100 years, we'll never be able to do it. And of course, they all say 50 years, 100 years. And I say, we've done it 5 years ago. I don't know why it's not more known throughout the world, the wonderful things that quantum computing is giving us at the moment. Okay, here's a complete overview. Now, if you know the process, please be patient, but this is for someone who knows a very little bit about quantum computing, but hasn't really looked at quantum teleportation. So there's the process on the right, and you can even see just by the number of gates and measurements, and there's only 3 qubits. It's not complex. So let me just read this out, and then we're going to talk about what exactly is happening. So Alice is a qubit. We'll use the Bob and Alice, of course. Alice is a qubit. She wants to teleport to Bob. So that's what needs to be done. And if we look now, let me take my annotation. So we're talking about, just give me a second. Can you see the spotlight?
Yeah, we see it moving.
Yeah, thanks. I'm just checking everything now for some reason. Okay, so we have 3 qubits. The top one is Alice's computer that she wants to be teleported. And then these bottom 2 here, so the bottom 2 are a bell pair between Alice and Bob. So Alice has a qubit, the top one, that she wants to teleport to Bob. Separately, we have to create a bell pair between Alice and Bob. There has to be some preparatory work done. You know, you can't just teleport something from here to 1,000,000 miles away. There has to be a bell pair set up, and that is where 2 qubits are entangled. And that can be done 6 months earlier. That can be done by Alice, that can be done by Bob. It's very easy to do. And later on in the presentation, I talk about how you create a bell pair. So what happens is they have a bell pair together, and Alice has a separate qubit that she wants to send. All she has to do, and now here we come to just a few paragraphs. All she has to do is she measures her bell pair, her part of the shared bell pair. So she measures what's the middle qubit here, and you know, it collapses to 0 exactly with probability of 50-50 of going to 0 or 1. But then what she does, so she collapses the bell pair, her share of the bell pair, and then that comes to 0 or 1. And then what she has to do is convey that information to Bob. And this is done classically. So it could literally be, I know this takes away some of the pizzazz, but it could literally be a phone call. She has to tell Bob whether she got a 0 or 1, basically, and plus or minus as it happens. But we'll talk about that a bit later, but that's all she's got to do. Then she applies the basic Hadamard gate. So again, we're talking about basic gates that people learn in lesson 1, and then measures it. A Hadamard and a measure, if you measure it in the standard basis together, that is the same as measuring it in the plus or minus spaces. And that's sort of the key to it. But again, all she does is a couple of transactions and she tells Bob what she's doing by classical means. So that's the important thing. That can be through fiber optic or any way that we can classically send the information. Let me just. So she sends the results to Bob, and there are only 4 combinations that she can do, because don't forget she's collapsing both of her qubits. And that's, she can say, Bob, 0, 0, 0, 1, 1, 0, 1, 1. And then according to whichever combination Bob gets, he applies a certain quantum gates or leaves it alone. So, which I'll be explaining. So again, he's just applying an X gate, which is a bit flip, or a Z gate, which is a phase flip, or he takes no action at all. But that is, and then once he's either taken no action or executed an X and Z gate, that's all that needs to be done. And that's, pretty amazing when you think about it, that's all that needs to be done to teleport the quantum information. And we'll get to this later as well, but that quantum information, is like in the binary world, it's like an infinite amount of information, because the complex amplitudes, are complex imaginary numbers, and they basically it's an awful lot of information that is somehow being teleported. So it really is unbelievable. Let's talk, okay, so that's, hopefully I haven't made that sound complex. That's all that's happening, a few measurements, a communication classically of what the result of the measurements were, and then an application of a few gates, and somehow the complex amplitudes of the original qubit have almost mysteriously ended up a long, long way away. So as you can see, a big thing about this was the Bell state. So let's talk about creating and sharing a Bell state. Now, I hope you can all still see this okay, but so the important thing, let me get my spine. So again, can you see me highlighting the qubit, Henning?
Yes.
Yeah, you can see it.
Excellent. Yes, so look, to create a Bell state, you need to take 2 qubits and apply a Hadamard and a CNOT gate, and I'll show you mathematically how that works. But the important thing, or one of the important things to understand, is that the state of the qubit, the initial state of the qubit, is very important, because there are 4 Bell states, and if the qubits are both initialized to 0, as in this case, so we can see the top one and the bottom one are both initialized to 0, then we actually get the 5+ Bell state. But if it was 0, 1, and 1, 0, and 1, 1, we get different Bell states. So we will be talking about that. Now, let's look at it mathematically down here, down the bottom. So what we're going to do is work out how a bell state is being created by just this simple application of a Hadamard gate and a CNOT. So we've got the 2 qubits initialized to 0. So the initial product state, which is just the tensor product of the 2 qubits, so it's just 0 times 0. The initial product state is ket 0, 0 that we can see down here. Now, when we use, so now we need to apply the Hadamard gate, and the Hadamard gate is only applicable to a single qubit. So when we apply the Hadamard gate, that changes the first qubit. Now, I like to show this, which is far more important than one realizes, because this shows which qubit we're talking about. When we have a ket, and in this case, we ket 0, 0, 0, the ket on the left is the first qubit. So, excuse me. So here we've got the first qubit needs to be replaced by the Hadamard gate. The Hadamard gate, acting on the first qubit, will turn it into this, within the brackets, this state, 1 over square root 2 ket 0 plus 1 over square root 2 ket 1. And if the, as we'll see in a minute, but if the qubit was initialized to 1, then it would be 1 over square root 2 ket 0 minus 1 over 2 ket 1. So that's the first expression after the Hadamard gate. So the product state, you still have to multiply by the second qubit. If we now move that out, we can see that it gives us 1 over square root 2 ket 0, 0 plus 1 over square root 2, 1, 0. Okay, so now we have to apply the, let's get back here, the CNOT. And I always like to just quickly say here that when we're talking about gates and I like to break it down into 3 things. We have gates, matrices, and microwave pulses. So what's really happening physically is that we're sending microwave pulses of different phases and intensities and durations to change the superposition. And we can do that logically here by putting on a gate, so drag and drop. You know, how easy is that? And what's that? So that's what it's doing there logically. Mathematically, what we're doing is just applying these matrices every time we drop down a gate. And these matrices are not that complicated. They may look very complicated to a beginner, but they're not really complicated. So when we apply a gate, what we're doing is multiplying by a matrix, and this is a bit of equipment that sends the actual microwave pulses. So I know that's a bit of a diversion, but I like to put that in so that people can see what's happening when we apply a gate. So to get back now to where we were after the Hadamard gate, on 2 qubits initialized to 0, we're now going to apply the CNOT gate. Well, the CNOT gate, the controlled NOT gate, is where we have a control and a target qubit. And if the, excuse me 1 second. If the control qubit is 0, we do nothing. If it's 1, we flip the target gate. So if I come down to here, this is where we are. This is the product state after the Hadamard. We can see that the first qubit is a 0. So nothing happens. The second qubit remains a 0. But in the second part of the expression, in the ket 1, 0, the control qubit is a 1. Therefore, we need to flip the second qubit, and that gives us this Bell state here. Now, is everybody okay with that? Because I don't want to carry on if it's totally confusing. If anybody has a problem, maybe shout out, because I don't quite have time to look at the chat. Sorry.
So hi, I have a question. I'm okay with what you've done so far. I posted this question in the chat and I didn't get a response. How entrenched in the notation is it that the top qubit in the circuit is always the leftmost in the ket notation? I'm used to doing it the other way.
Oh, are you really?
Well, I mean, you could do it either way. That's
Yeah,
not,
well,
I'm just curious. Am I doing it the way that nobody else does it, or?
Yeah, wow. You wouldn't think there would be a huge standard on that. Does anybody else have a comment? Maybe I'm doing it differently here from the way you normally do it. But yeah, I always have it, and what I've read and all that, if I remember rightly, it comes, the leftmost is the first qubit.
Yeah, I guess the reason I'm used to doing it the other way is because I call the top qubit Q0 and the bottom qubit Q1. And then I can think of it as 2 to the 0 and 2 to the 1. So it's a binary number. So I just find that convenient.
Yes, good idea. Well said. Okay. Yeah. All right. Well, thank you for that.
Well, whatever, either way, as long as it's consistent.
Yeah. Well, that's exactly right. There's many ways to do it. So that's wonderful. Thank you. And look, that's just giving us the 5+, and that's one of the 4 states. So look, I've now done the same thing, but the second qubit is initialized to 1. So look, the multiplications and all of that is the same. And that comes to the second Bell state, which is psi plus. And on it goes to the 4 Bell states. And we can see that on the left, the phi Bell states of plus and minus. The important thing here, if we were talking, let's say, photons, you've got the polarization of both qubits is the same. When in phi plus or phi minus, it's just the rotation is minus. So the rotation's opposite, but the polarization is the same. And if we look on the right-hand side under psi, we can see that the polarization is different. And this, and then in the case of psi minus, which is the different one from all of the others, the singlet, it's because it is opposite in polarization and rotation. So it's very interesting. Now, I just want to give a quick overview of the rotational invariance as well, because that's important and explains why it all works, basically. So if we look at what we got to before, we can see that we can write out the Bell basis and the computational basis, the 0 or 1, as we have done, but we can equally do it in the plus or minus. And we can equally then do it in what we call U and UPerb. So it's in any basis. So, and there's a relationship between the bases. You see, the thing is, when you collapse a Bell state, you're doing it to find out what state it's in. What you want to know is what's the state, which of the four states is here. So let me just show you. So we've got the 0 and 1 qubits, so it's in the computational basis. If I now introduce a random basis, so all we're doing, if you like, is rotating the superposition, rotating the measurement basis. When I talk to some of my students, I say, and it's not a great analogy, but I actually say, imagine, remember the old Rubik's cubes where you used to be able to rotate one side, so you could turn it on its side, rotate it, rotate a row. You know, this is similar sort of thing what we're doing here. And so now we've rotated the basis. So the question is now, if I still measure this, the first qubit in the computational basis, the 1 or 0, if I get 1, the second one qubit will always be 1 with 100% confidence. If I measure in the UPerb basis and I get U and the first qubit, the second qubit will always be U. So, you know, the point I'm making is not just limited to 0 and 1 in the computational basis. So now the question is, what if we I've actually just gone over that. Okay, what I'm going to introduce, and this is the important thing, and this is the invariance of the Bell state. If I introduce another basis, V and VPerb, the question now is, if we measured the first qubit in the basis U and UPerb and we get U, what will happen to the second qubit? Well, if we measure it and get U, the state of the new system will be UU. So if the first qubit's U here, the second qubit will automatically go to U as well with 100% probability. So, you know, the second qubit's going to measure U. Oh, I thought there should be a few more slides there. So now what's the relationship with V? Well, we find that there is a relationship, which is remarkable, to be frank. And the relationship is that what we can do is take the angle between U and V, and the probability that the second qubit is going to be V is cos squared theta, if we use theta as the angle. So whatever the angle difference there is between two measurement bases, there's a connection between the results. That's the important thing to note. So one can see how there could be, this can be manipulated in the teleportation game, because what we're basically doing is rotating and manipulating the qubit, then reversing that operation. At the end of the day, effectively, that's what we're doing. And we introduce gates to do that. So that's what's actually happening behind the scenes, if you like. So let's now look at in a little bit more detail. So we're looking at the wave function that Alice wants to send to Bob. And that wave function is psi, alpha kept 0. So the probability of it being a 0 is alpha, which is a complex amplitude, plus beta, another complex amplitude, and the probability it's going to be 1. We don't know the value of alpha and beta. And of course, we can't measure it because as soon as we measure it, the function will collapse. So we have to think of a way of sending the two complex amplitudes without measuring them. Now, if we were in the one laboratory, so we didn't have to go over the great distance, and we had a channel between the two, what we would do, we could put a C0 between the two. So again, let's look at what we've got here. We've got Alice's bit and Bob's bit. And if we do it, we can have the product state of the two of them. So we could multiply that out and then apply the C0. And again, the C0 will change the second qubit, the target qubit, depending on what situation the control qubit is in. And basically, if we multiply that out, the C0 will change the second qubit from a 0 that I have here to a 1. So, I mean, don't worry about the maths. You can go over this if you like, but the important thing is we have an entangled state of 0, ket 0, alpha, ket 0, 0, beta, ket 1, 1. So that's not what we want. We want to get at Bob's end the original alpha 0 plus beta 1. So we're not getting that. Now, what we could do is we could measure the qubit in the computational basis, but if we do that, it will collapse to ket 0, 0 or ket 0, 1, 1 with 100%, with 50% probability of either way. And that's not what we want. But amazingly, and this gets back again to the rotational invariance is why we can do this. But if we measure on the plus or minus measurement, or the sign basis it's sometimes called, so we're rotating it, what we first need to do then, we've got so we know how we can get alpha 0, 0, beta 1, 1. Now, if in the sign basis, a 0 is replaced by 1 over square root 2 ket plus 1 over square root 2 ket minus. And so we have that, and that's multiplied by the second qubit, the 0, 1. And we have it plus beta 1 over square root 2 plus minus 1 over square root 2 ket minus, and that times the second qubit, which is a 1. So again, we're just doing the same thing as we were before. If we multiply all that out, we get the bottom line. And we get the new state. So the new state equals this expression plus this expression. Now, just by extracting the 1 over square root 2, we can get the new state, which is Alice's bit. So we've got the first bit here, outside the brackets is Alice's bit. Let's say she measures in a positive, then Bob's bit will mysteriously, miraculously be psi. So this is why Alice has to measure it, and if she gets a plus, she tells Bob, hey, Bob, I've got a plus, so your qubit is equaling psi now. Leave it alone. If it's a minus, what we need to do, the Bob's qubits in state alpha ket 0 minus beta ket 1, and we have to change, that's not what we want. We need to change the rotation. We need to change the phase. We need to do a phase flip, and we do that through a Z gate. So again, when she communicates to Bob, she says, look, I got a minus, you need to apply a Z gate. Again, it's important to realize Alice doesn't know the value of alpha and beta and cannot measure them, cannot find them out. You cannot find it out. So now what we're going to do is the same process, but over a large distance. And this distance could be theoretically, millions and millions and millions and millions of miles away, as long as the end destination place has a bell pair connected to the transmitting place. So, okay, so how can we do this? We can't do a CNOT gate because there's no channel, and we're talking millions and millions of miles. But what we can do is apply a CNOT gate to both of Alice's qubits. So here's the CNOT gate to both of Alice's qubits. Remember, she has one qubit, which is what we want to teleport, and another one, which is it's part of a Bell state with Bob's. Now, the important thing is that these two are one. Non-locality, that's what quantum entanglement is all about. Non-locality, somehow you can't describe these individual qubits by themselves. Okay. Now, again, it's the same math, so it's not too difficult. Let's look at what the state was before Alice applied the CNOT gate. So here we've got Alice's qubit, we want to teleport, and here we've got the Bell state, which encompasses both Alice's and Bob's. We multiply them out, just like we did before. We apply a CNOT gate, just like we did before. Bear in mind, now this is where you've got to look at, if the first one is 0, then which qubit's 1, which one's 2. 2's easy because it's in the middle, and which one is 3. So the question is, if Alice, or the issue is, if Alice measures 0, so this is the statement that we had before after applying the CNOT. So if hers is 0, sorry, and we have 0 here in the first qubit, so the one on the left, sorry. If she measures 0, and then we follow it all down, we get to this entangled stage, which is what we want. We're getting to alpha, and Alice's qubit. So right down the bottom, alpha 0, 0 plus beta 0, 0. So now Alice's qubit in her laboratory is entangled to Bob's qubit. If she measures a 0, excuse me a second. Oops. If she measures a 1, then the 1 is, again, just construed the same way mathematically, and it comes to alpha ket 0, 1 plus alpha ket 0, 1, 0, and beta ket 1, 0. And that's not what we want, but we can get to it by merely applying an X gate. So doing a bit flip. And then if we do that, we get to this Bell state entanglement with the qubit we want transported and Bob. It really is amazing. So let's now put it all together. And we can see that in our, so we have, just like I said at the beginning, all we're doing is having one qubit we want teleported, and we have to have a Bell state between 2 other qubits. We then apply a C0 gate, and we measure it, thereby collapsing that qubit. And then all the mathematical stuff follows on from our previous slides. Alice then says, if she gets a 0, leave it alone. If you get a 1, apply an X gate. And then we're in a state of the original photon to be teleported, or qubit to be teleported, and Bob's is now in a Bell state, the psi plus, the phi plus Bell state. Oh no, we don't know that, sorry. It's just in a Bell state, we don't know which one. But we know that if we apply a Hadamard gate to Alice's original qubit and measure it, as I mentioned quickly before, if you apply a Hadamard gate and then measure in the standard basis, that is the same as measuring in the sign basis, in the plus or minus basis, which is what we did, if you remember rightly, to get back to Alice's qubit. And if we do that, and then Alice measures it, and she tells Bob, and Bob takes action either way, believe it or not, what will be left after this reversal of the Bell states, if you like, what will be left is the original side. Wow. So let's look, basically that's it. I would like a bit of a discussion on this. If I can, I just want to check that. That's right. Oh yeah, this is my final slide. So, okay, I'd like to put it to the audience now. When was the complex amplitude information for alpha and beta, the complex amplitudes, transmitted? Can someone try and tell me when that was done? At what stage? Because like I say, this is extremely complex information. In the binary world, to describe a complex number, theoretically could need an infinite amount of binary information. Yet somehow, Alice, without knowing what alpha and beta are, has transferred that. Can anybody try and give an insight into that? It's okay if you can't, because, one can't. Any comments?
Okay, I'll try.
Thank you. Can you identify yourself first, please?
Okay, my name is Eamonn.
Yes.
And I think this, alpha or beta transmit will be after CNOS applied. And I do have a question if that is true.
Right, okay. All right, well, look, we can get to the questions straight away. I think, I guess, look, we don't know is the answer to when or how the complex amplitude information was transmitted. It's all down to the wonder of quantum entanglement, which is underpinning the Bell states. But again, I mean, quantum entanglement, we all know spooky action at a distance and all of that. But it's allowing us to do this. And quantum teleportation is a part of quantum cryptography. It's used all the way through. It's an amazing process that we can use. Yet, you know, we don't understand what's happening at a fundamental level. It's amazing. And before, Eamonn, we get onto your question, the second point here, we may as well cover that. It's a completely, when we talk about the 4 classical, remember the information that Alice sends Bob 00, 01, 1011, that is completely independent of the actual complex amplitudes of psi. That's a probability of 1 in 4. So Bob's actions are, if you like, completely probabilistic. Bob's actions are a 1 in 4 chance, but that 1 in 4 chance can apply to any qubit, not just Alice's. The actual information in Alice's qubit, the classical combination has nothing to do with it. And I find that really fascinating. So, you know, there we are. So look, if I can end it there, I'd like to thank you all. I would like to mention my YouTube channel. Like everybody in our industry, we need subscribers to a YouTube channel. There's lots of great information there. Anna, who's in the audience here, her and I are beginning to do a few things on our channels, like talk about other people's presentations that are quite difficult, and then discussing them in small groups. So there's a lot of information you can get free of charge on the channel. So Henning, did you want to ask for any questions, or how do you want to take it from here?
Well, I certainly would just like to open it up for discussion a little bit, and maybe also expand on how this teleportation, this entanglement really is kind of like the core resource for quantum information science. You already mentioned that we use it for cryptography. Really the whole theory around quantum teleportation has been kind of generalized when you look at quantum channels and basically kind of like a quantum Shannon theory. So just like we have a very rich theory when it comes to understanding what kind of capacity you have when transporting information through a classical channel. There's a lot of research done on basically what it means if you can add a quantum channel and quantum resources to your classical channel. And there's a lot of interesting questions around that one. I mean, one, for instance, that comes up a lot is, well, can we use this to communicate faster than light, which is just obviously the old paradox that Einstein first was throwing up. So anyhow, I just want to throw out some of these aspects and just see if there's additional questions in the audience.
That's wonderful. Can we just take a 2-minute break?
Absolutely.
Yeah, thank you. Only be 2 minutes.
No worries.
Okay, wonderful. So do we have any questions? Oh yeah, Amy did have one.
Okay, my question was firstly when you at beginning you mentioned about teleportation. So that quantum state Alice sent to Bob, how those quantum state sent to Bob through optic fiber, but you do say we don't have a quantum channel. So is that how those quantum states sent to Bob? Second question, related question is, where is that C note located? During this transportation process, I assume it's between Alice and that quantum state on the way to Bob. And then if that C note is man-made, that still is not absolutely secure.
Great questions, Yining. Thank you for them. Okay, so first of all, the bell pair can be created anywhere and sent through any medium you can send a photon through. So fiber optic, it can be sent if you're using electrons. Again, it doesn't matter which quantum particle you do. Some are like the polarization characteristic of photons works better than the spin of an electron. But yeah, so you just send it by normal means as you would send any communication. So that's that one. And the C naught is between, if it's the one I think you're referring to, is when the C naught gate is applied to Alice's qubit and her share of the bell pair. So when I was saying before that there's no channel, there's no channel between the teleporter, the area, the transmitting area, and the destination. There's no channel between them because they could literally be a million miles away if the other proprietary work has already been done. So there's no channel there, but there is a channel in Alice's laboratory. So when she connects the qubit she wants to teleport with the bell pair, that's done in the normal way in her laboratory. Does that answer the question?
Yes, but if the quantum state is sent as just a traditional way, what is the role of satellite here?
Does anyone want to answer that?
I think one of the things that I'd like to say is that even between really far separated particles, the space is the channel itself. Free space is the channel. So there's always a channel. Free space is the channel. And, the second part was about the satellite. And with regards to satellite, the satellite itself, and this is where the entanglement comes in. Your particle or whatever information you're referring to at the ground state is entangled with the satellite. And that satellite is entangled with another base station, perhaps in Sweden or somewhere, one in China, one in Sweden. And that's what's happening, really.
Thank you very much. That was a very good answer. Thank you.
Hey, Eamonn and Barry, I wanted to basically go back to Barry's question of how firmly entrenched is the notation that the topmost qubit in the circuit is the leftmost qubit in the ket. And I wanted to go back and I wanted to think aloud here. Is it something we can basically answer with the same simple quantum entanglement or quantum fact conundrum, where we say, as a very classic example, when you have two socks, whether it's a left or right sock, which one it is, and you could use them interchangeably. That's the same piece here. We could use them interchangeably because one fact is there that in both the cases, we were able to arrive at the same result. And if I extend this quantum fact conundrum little more as an example, and I say, if you are two friends sharing the dormitory in the college and you went for different college trips, and then you realize that one pair of socks got split, one left sock went to one friend, right to the other friend. By the time you realize that you are left with only one socks, how do you know whether that is a left sock or a right sock? But at the end of the day, and it's like basically how much time you had to wait before you said it left or right. Because either ways, when you see it's missing, it's missing. And if you had whatever way, you have one sock there. So same is the situation here in terms of entrenchment, which we are looking at, whether it's the leftmost or the rightmost. But at the end of the day, we are arriving at the same result when we do the full computation.
Yeah, we just have to be very careful because I've
Yeah.
gotten myself into really bad corners teaching this, where at one point I used one convention and the other point I make my, and then,
Right.
you know, standing in front of 30 students and they're all pointing to me and saying nasty things. So I don't think that this is a deep issue, not at all.
No.
Just my curiosity about the way it's normally done. Can I pose a different question? So I do teach this, and I find with almost all of these phenomena, teleportation and Deutsch's algorithm,
Yes.
I just don't have a way of making students visualize it. The math works. And then when you try all four possibilities, it all fleshes out. And I can do the block sphere if we're just doing one qubit. But as soon as you have two qubits, I don't have a way of making this look like anything except a coincidence.
Wow, Barry, that's a great statement. First of all,
Well,
thank you.
are there any, please, a magic formula?
And I wanted to ask that question to everybody. Can anybody answer that? Because yes, it's so difficult to make it visual. Sorry, Henning.
I think.
Excuse me, I have an idea. Sorry, I'll wait. Go ahead.
Well, I want to go back to the Rubik's Cube that was earlier mentioned, because that's typically an example that I use when I'm trying to make people visualize it in some way. But the challenge here is that we are already on a two-dimensional space with the topology of a sphere when we just have one qubit, and then if you entangle one qubit with another qubit, we essentially have a four-dimensional sphere to work with. But it's always just a sphere. That's why we always deal with rotations, essentially, when looking at the operations that any quantum gate is performing. So in a sense, I try people to imagine a Rubik's Cube that is more than a cube in three dimension. Basically, try to imagine how a Rubik's Cube would look like if you project it from a multidimensional space down into our space. It gives a little bit of intuition why this thing is looking so complex, although the mathematical underpinnings are so simple. Because again, if you're just rotating a state vector on a multidimensional sphere, the math is easy, but the kind of trajectories that you can get are very, very complex. And that's basically as far as I can push it, because our limitation really is that we are just creatures that live in a three-dimensional space, and that's pretty much as far as we can visualize things. But any trick in the end is, you're projecting it out into lower spaces, and try to basically make these shadow puppets of a hyperdimensional structure by projecting it down to three-dimensional space.
I just posted a alternative approach to that question. I know, I imagine a lot of you people are familiar with Terry Rudolph. He's the R in the PBR theorem. And Rudolph is also one of the co-founders of PsiQuantum. Well, if that's not enough, he also has this passion about teaching quantum to high school kids. And you'll see that book in there, Q is for Quantum. That's his book. And it turns out, I'll put the post in. I'm doing an event in Austin with Scott Aronson on Monday. And if you RSVP to that event, you get the book for free.
Wow.
Terry agreed to do that. So wait, in a minute, I'll put that in the chat. Give me a minute. But anyway, that he takes a diagrammatic approach. And you know, he's a major guy, so he makes this statement: I can teach quantum using only high school math. Wow,
Yes.
really? But that's the claim he
I
makes.
know what high
He's
school
a
you
major
went.
guy, and he actually pulls it off in that book to some degree. So you might want to look at that as a teaching technique. It's all diagrammatic and only uses the distributive law. So, all right, hope that's helpful. Give me a second. I'll put the link to the event. And even if you don't go, RSVP, you'll get the book. So, you know, it's well worth the 2 minutes it takes.
Yeah,
I hope that helps.
I was just gonna say that on the IBM quantum experience, when you develop a circuit, basically you can, you know, in case you didn't know, you can make your own circuit on the IBM quantum. And you know, it shows the sphere, the block sphere for more than one qubit, for all of the qubits that you have. Now, it didn't make a whole lot of sense to me when I saw that block sphere for more than one qubit, but it may make more sense to you or your students. So maybe something to look at. And then I was also gonna say that.
Sorry, excuse me. I was clicking a link and got all carried up while you were talking. Are you talking about still talking about the Q as the quantum or something else? Because I want to hear it if you're talking about something else.
Okay, it's IBM quantum experience. I don't know if you.
Yeah, sure.
Oh, okay. So when you design a circuit, it shows the block sphere of all of the qubits on just one sphere.
Okay.
So you may want to look at that. That may help visualizing. I don't know. It may help.
It's worth a try.
Yes. It's definitely worth a try. And then, have you seen the movie? It's called Flatland.
Of course.
Okay.
Well, I mean, read the book.
Okay, you read the book. Okay. So that's got some analogies. Might be helpful for you.
Okay.
Excuse me, I just posted that link, but I hope somebody tries it to make sure that it works. I'm not sure if the chat will.
I'm going to try it right now.
Yeah, let's confirm that it works.
I wanted to. Nathan, that's wonderful. Thank you very much for providing that.
Works.
Yeah, no, it's a coincidence. I was late for this session, and some of you guys know that we're doing that event with Scott Aronson. So it might be worth attending. You know, Scott's another major guy.
Oh, of course.
Nathan, the link is working.
Oh, great. I'm good to know. Thanks a lot. Use it. And I'll just turn off my speaker now.
Thank you,
Charlie
Nathan.
has a question.
Thank you.
I got a question. What, besides quantum cryptography, what applications what are the applications for quantum computing with the quantum teleportation?
It's almost in every area. Certainly security is the big one. I think there's an awful lot happening in the background, you know, with the government and the military on uses that we haven't even considered yet here. So it's, I just think it's the bedrock of almost everything. And I wonder how it's being used in the military and, in high-end governments. Does anybody else have a statement on that?
I think I can have a go at that. So firstly, going back to the first question, which Barry asked earlier about, how do we teach this? How do we visualize it? I think coming from a student perspective, which is where I was, right? When I started learning physics in my high school, I loved my professor because he used to show us a vision rather than mathematics. It is the mathematics that actually corrupts the physics. So what I meant by this is like, you can literally pick up the mathematics. It's very easy. And, you can address a lot of things by mathematics. But by going it the mathematical way, you actually miss the actual essence of what we are trying to do. So if you're involved in teaching, try to create the magic behind it, because it is magical.
Yes.
Do not even touch the equations. Equations are the last thing when it comes to proving the situation. Because if you introduce equations early on, or you go, your whole thing becomes about proving and verification and all that kind of thing. And that basically devoids anybody from the mystery of what is actually happening. So one example, somebody mentioned flatland. I've not read it, but I can understand what it's trying to say, right? You got two-dimensional space, you got Hilbert space. But when we say the word Hilbert space, what does it actually mean? And it is so easy to, because whenever people talk about Hilbert space, they will literally write down an equation. That's what Hilbert space is. But what does it actually mean? Well, because what are we trying to describe? Mathematics is just a codification of whatever we are observing. So this is the most important thing. I think from a teaching perspective, do not go for formalism. Formalism constrains the whole idea. It constrains science. Formalism comes later on to define and solidify an idea, to justify what's happening, to create some kind of formality in the rule system. So this is what I will say. And with regards to the second part, what are the applications of quantum teleportation? As you rightly said, it's in security, yes, but there's also quantum radar, for example, in military you mentioned.
Yes.
So, so each of the, how do you detect a fighter plane, a stealth fighter jet, for example? There is also quantum gravity sensing. So, for example, before people used to, carry these planes, which will carry a magnetic anomaly detector and measure what's underlying the ground, or ground penetrating radars, for example. So right now, again, one of the university in the UK, we've developed a quantum gravity sensor. Essentially, it measures how the particles are actually falling based on the gravity. And that's also related to the quantum teleportation. There are a lot of other, so there's lots of physical applications that are coming out. And as you rightly said, there'll be many more that'll keep coming. That's all from me.
That's a beautiful answer. Well done. And obviously, I don't think anybody's going to disagree with your suggestion that we stick to the beauty and the mystery of all of this. And I suspect that most of us really do. The maths is just, should be the last recall. But certainly, when people ask me something like, what's quantum teleportation going to be good for? I normally say what is called, I don't know whether any of you have heard this expression, the unk, the unknown. As in, this is so unbelievable that, we could take a couple of centuries to come up with something that we could use it for. It is absolutely amazing. And if I may, I just wanted, Virendra, if you're still there, I just want to answer your question before because we sort of all got waylaid. But the socks and all that analogy that you're talking about, you're almost talking hidden variable stuff. And I don't know how aware you are of Bell's inequality and how the CH-SH game and how it's been proven that it's spooky. So I didn't know whether we could have gone down that path. When it comes to the nomenclature or the standard way that we should measure, that we should depict the qubits, I don't think we can just leave it. I think there has to be one universal standard, like there is in anything. I'm amazed that there isn't. I would have thought that I mean, I'm going to really check.
What universal standard? Excuse me, I missed that part. What universal standard?
Okay, and Nathan, what we were talking about, I showed the. Do you know the way you've got you may have ket 0, 1, 1.
Yes.
And the 0 is the first qubit.
Mm-hmm.
And the one in the middle is the second qubit, and the one on the right is the third qubit.
Right.
Is that a universal standard? I thought it was.
Oh, okay. Interesting. Thank you.
I created a monster. I didn't mean this to be any kind of a reasonable issue.
And quantum is a monster. Don't worry. We have so much of unknown stuff when it comes to quantum. After all these years, no matter what advancement we have made, we still have lot of stuff.
There's no agreed upon notation in any field, unless you have people who are insane running it. I'm just curious about, not doing exactly the opposite of what everybody else does. I don't know.
I don't know.
But there's still an advantage to being what's the word I'm looking for? Ambiguous. You having to have a tolerance for ambiguity.
Yeah.
When you pursue quantum, and the idea, but the other part is, even under that, all of us, like, how many are in this event? 35, 40, and some of these other quantum meetups that are going on now all over the world. We all have a great start, because knowing something someone else doesn't, which is the state we're in a sense, gives us a huge advantage when 3-4 years from now, when quantum actually becomes commercially viable, even 5 years, assuming that happens, and it's reasonable, it looks like it will, then all of us who are suffering through this ambiguity will be a huge step ahead. Imagine what the people who aren't even familiar with quantum can do, right? So
Correct.
In 4 or 5 years, it's a huge advantage. Peter Thiel, you might have heard of him. He's like one of the top
PayPal founders.
Yeah, not only that, PayPal and a bunch of other things. Anyway, he invested in Facebook $250,000, and 8 months later he got back $3 billion. Really, it's no one ever got it that far. So the reason I say that, he's a super smart guy, and that's his thing. When you try to pitch him, he'll say, "Listen, I don't want to see PowerPoint. Here's what I want you to tell me. What do you know what other people don't?" And when you think about it, that's what all these major people like, Ellison and Zuckerberg and all the others who started these major companies, they knew something somebody else didn't 3 years before the general public.
And
that's my point here. We're all suffering through this ambiguity, but the reward is going to be, assuming, of course, quantum is practical at some degree, we'll have a huge head up on everybody else.
And that's absolutely very well said. And let's not count Elon Musk's money, what he made out of Tesla and SpaceX. To make.
Yeah, right.
Yeah.
Knowing something others don't, that's my point of it. I just wanted to give him credit for that statement.
I mean, the guy who really invented the electric motor, the Mr. Tesla, did he ever imagine those days that this is going to be a game changer someday later, 100 years or whatever number of years later?
Yes.
Yeah, I think he died broke.
Of course, one of the Apple founders also was collecting pennies in Las Vegas. He also bailed out early, and we can see where Apple is today. First $3 trillion company.
And even Tesla has had his close calls with money. I mean, they were with both operations, SpaceX and Tesla itself. They were right on the brink of getting through. So.
Absolutely, they were right at the brink of disaster. And the way he has turned around, the way he's still playing the whole game with splitting of the stock and everything else, which is going on now. And he has something to entice investors back in when he sees something is kind of slowing down. That is the beauty of the guy, over and above everything. And as I think Nathan was saying, that the ambiguity which he has played very well, right? And then he brought in crypto also into the game, Bitcoin's investments into Tesla's. Everything he mixed together, everything was ambiguous. We still know there is a lot of ambiguity around crypto. 5 years later, yeah, and I'm not trying to diverge from the topic.
To quantum.
Yeah. I'm not trying to diverge from the topic and bringing it back to our topic of the day. But yes, those are ambiguities which people got paid off. And go to another side of the story. You may call it gambling. You might call it risk and reward ratio. Everything is there.
One aspect that hasn't been mentioned here, where quantum teleportation is key, is called blind quantum computation. That is something that really differentiates it fundamentally from classical computers, because when we teleport a quantum state, we don't really know what's in it. And measuring the classical information that Alice sends to Bob does not allow us to infer this either. So it's really a complete safe transport information. And obviously that's used for quantum cryptography, but it can also be used for something called blind quantum computation, where essentially you can prepare data and an algorithm, and you can teleport it to a quantum computer and have it processed there, and then have the results teleported back. And because it goes over the quantum channel, you can actually have these algorithms being performed on the quantum computer without the quantum computer itself knowing the results that you get back. So it's essentially a way to have remote computation performed in an absolutely secure manner, which of course, in the, when it comes to big data and to data security, is going to be, I think, a very, very important aspect eventually.
Well said, Henry.
Just wanted to throw that out as one major application that I see coming in the future.
Okay, may I ask a question?
Yes, of course.
Okay. Wave function is not enough to describe the initial state of Alice. How do you apply the density matrix as the Alice state and prove the teleportation work?
I'm sorry, I don't understand the question. Could you just say it again, please?
Oh, you just replace the wave function by the density matrix.
Oh, by the density matrix. Okay.
Yeah, that's like the Alice. So then prove the teleportation work.
Wow, can anybody answer that one?
Well, I'm not sure that I understand it completely, but I mean, you typically work with the density matrix if you have also classical probabilities in there. So if you have a system that's thermal as well, and it's not 100% quantum, then you get classical probabilities in your interdensity matrix, and that makes the whole thing a little bit more tricky, because if you want to teleport a state like that, where you have classical uncertainties in there, you have to error correct for those. So you will need essentially a bigger pipe, more, I think, so on the classical side, that kind of goes into this whole quantum channel theory field, which is, I know just a little bit about, enough to maybe make myself dangerous, but essentially what it comes down to is, my understanding is if you work with the density matrix and you have these kind of not pure states, then having the capability to error correct on the end is the biggest issue.
Okay.
Don't know if that answers the question, if I understood it correctly.
Yeah, the density matrix or density operator, same thing, tends to be used when you have, I forgot what you call them. It's like a certain, certain kind of states when you have like mixed states, right?
Yeah, mixed quantum states, exactly. Yeah, that's where you have classical probabilities now as well.
Yeah, so the idea behind that is that, you know, you prepare a certain state, but you don't know that all, I mean, you prepare a bunch of particles, but you don't know that all of those particles are like in exactly the same state. So you have like a mix. And so you have something that instead of like a definite wave function where you like, you know, you assume there's a definite wave function, you have some kind of a density. So some kind of like an average over like these different states that the different particles could be in.
Yeah, because they are noise. So
yes. So density matrix, it tends to be used a lot in the literature. I'm thinking because it's more realistic experimentally, because, you know, experimentally, a lot of times, you don't know the wave function. And so instead you have some kind of a statistical sort of knowledge, and you know, you use the density operator for that.
Yeah, you typically prepare an ensemble of states, and you don't have 100% certainty that you actually prepare the correct state, and then you basically have to model the probability for getting it wrong, so to speak.
Yes.
Okay, thanks.
So in the beginning, you don't know what the state is. When you start, then you kind of, if you don't know where you're starting, then how are you going to find out what your end is? Maybe I misunderstood that.
Yeah, it's kind of like calculating all of like the different scenarios, all of like the possible different wave functions that you have, and getting some kind of like an average. That's kind of what they call it, like a density matrix, density operator.
I mean, is it something you are alluding to? Obviously, the density matrix comes into play when we say that at infinite temperatures, all these y's are equal, and density matrix becomes a unit matrix, essentially speaking. So beyond a temperature value, everything it doesn't make much difference. Is that something like a generalization that comes into play for easy, I would say, accrual and summation of all these unit matrices?
Well, it's the density matrix. It's the off-diagonal elements are the classical bits. Is where the noise comes in. If you have a diagonal, if you only have values on the diagonal of the density matrix, then it's a pure state.
Right.
That's just the underlying formalism.
Now that definitely is mathematical.
Yeah, it certainly is. Yeah.
purely getting into full matrices, vector algebra.
Yeah, I mean, essentially, it's a tool where you're looking at a physical system, and you're essentially then trying to work out a quantum state of that system. So, in a nutshell, it's a mathematical operator, and that is you're just calculating all the probabilities of the outcome of any measurement that you perform in that system. And,
exactly. Yeah.
And when we say classical, it's quite an interesting thing that nowadays, because of the because nowadays a quantum computer is a real thing, and I see nowadays people use the word classical so loosely because in actual physics, in quantum physics, in regular physics, there is no such thing as classical in the sense that it is used in the sense of computers. In quantum computer, when you say classical, it has a certain meaning, which is the binary 0 and 1. In physics, it does not mean any of that thing because it's because does that mean that classical computers don't use quantum phenomena? Of course they do. Your whole Valley functions, your what do you call it? Your quantum tunneling, for example, your transistor using that. Those are all quantum phenomena. But when we say classical, I think in physics side, we are essentially describing what people are meaning to is Newtonian physics. Whereas in computer science, classical means 0 and 1, binary notation. So I think there are a lot of mismatch that people use interchangeably, and it confuses everything. And that's something to watch out for.
Yeah.
Very true.
And I'll cite a very simple, it's more of a comment from student days. So I was the one who came from physics side into computers and then AI and machine learning. And now I'm trying to explore the quantum for the last few years. But going back to students' days where I'm trying to bring this comment, our professors, they had a constant fight because those were the days when computers were in the budding situation. They were like, the hype was getting created. I'm talking of early 90s when it was kind of the state of affair where we are today for quantum. That was the state of affair where computers were, I'm sure some of us on this forum must have used the real floppy based computers where you had one boot floppy and one floppy to work with. And then from there you transformed and transitioned into basically disk-based systems and beyond. But the point I'm trying to make is the fight which those professors in mathematics and physics department, they used to have, and both used to claim, we are responsible for the origin of computers. I'm just reminded of this, while we heard just what we just heard.
For those of you who are like in my age bracket, in my 70s, you might remember, or up in that age range, in the 1970s, 60s, when IBM came out with Big Iron, right? This whole new computer system, PL1, Programming Language 1, the first software that had 1 million lines of code. And that was to make the machine easier to use, Fortran, COBOL, which is why people bought the machine, so to speak. We haven't reached that era yet in quantum computing. You might remember Ross Perot. He was like one of the first real tech billionaires in the 80s. And the way he did it is to go to the machine people and say, look, you don't know the machines. I know the software. Hire me to do your stuff. And he was like, what Larry Ellison is doing now. The point I'm trying to make is the Ross Perot of quantum computing is yet to appear, right? And that person is likely, or the Bill Gates, so to speak, to put it into the 1990s. And that person's probably in high school right now or an undergraduate. But
maybe
that will make a big difference when that.
Yeah, that's very rightly said. Very rightly said.
I think on that basis, what I will say is I think while money is important and money is really, what makes everything. But I think if you look at, from my understanding, from where I am, right? And I think from where I see it is that you can always earn money provided you have a passion for something, because then you will find the use cases for it. Because even when computing was in your days or in, Virendra days or whatever, right? You guys were the early pioneers, right? And there were loads of people doing computing, but it is Bill Gates' idea to give this computing to the masses, because Apple computing or the computing device is still for the very selected few, right? So it's somebody finding Elon Musk, for example. He loved coding. He had a passion for coding. That's what I read. In South Africa, he was already writing a website and doing some and selling some stuff through the website or something. And likewise, these guys at Facebook, they were developing this in their college. So the thing I'm trying to say is that, yes, all of this is good, fine stuff. And, earlier people mentioned we are the early pioneers. The point is not that. The point is, where is the passion? What are you going to do with it? Because if you don't have the passion, if you don't have the use case, then it will be, you will use it and you'll make something out of it. But people who have passions and people who have a use case out of it to solve real problems are the ones that will truly make money out of it. And, these companies.
Zoom caller, who are you? All we see is Zoom caller. You say.
I'm a Zoom caller.
Right.
Yeah.
Can you put it? Can you put your who you are in the chat? It's some interesting.
Yeah. Allow me to finish this one moment,
please. That's all. Yeah. Of course. Sorry.
So what I'm also saying is that the big blue, which is IBM has been, in there for a very long time. IBM sold, its ThinkPad business, Lenovo, to the Chinese, right? And everybody thought IBM, which had a research budget, which was bigger than the, budget of many countries, will go, that's it, IBM was done. But here is IBM reinventing itself into quantum computing. And you have Microsoft, which is a leader in classical computing, and you have Google, which is a leader in your, non-Microsoft computing, and you have Apple, which is a leader in consumer side of computing. They're all investing in quantum computing. Why? Because they see a great potential. And as a business, they have to keep themselves ahead and all that. But we are the truly beneficiary of this technology, because we are the guys who are going to be consuming it. And it is up to us. What passion do we have and how we use it to solve the world's problem? Because only when we solve certain problem that people are able to use it, that's going to make a lot of money for some people who are able to have that passion. So passion, I think, is more important than any other thing. If you love the subject, you will find numerous ways to, kind of use it, abuse it, or whatever. And that's my view. Anyway, with regards to the money side of things.
That's very, very true, because unless you have the passion, you're not going to get there. Unless these people had the passion to really exploit that technology. And when I heard the story of all those floppy-based computers or other computers which I've shared today, and also when we got to the thing, all of us have seen that transformation. What we studied in college, we never got in the field. Why? Because by the time we were in that, any job or any next job or any next effort and endeavor, technology had moved a couple of steps ahead, because that's been the passion which is driving all these things. And when we all have seen, whether it is GitHub kind of situation or open source, or the way Google gave it away for open source and all these subjects, all these things, where we used to write so much bulk of code earlier days, now all that piece is available as a single library command. And that's what, when I was doing my research, also I was hearing the same thing, and my guide used to tell, and I remember him for that always. He said, you are putting this effort, you're putting this algorithm in place, you are putting this coding in place, but be mindful that by the time you will see this productization or anything will happen, people will be using it with one simple library call, and that's happening everywhere. And then obviously the complete hardware, I would say what we call in terms of physics is that bursting point, that when this technology has burst, all these possibilities are there for compute and all these powers, so that you got CPUs and TPUs, GPUs and TPUs, that has made all this AI/ML possible. And now quantum is what people are trying to exploit, and with all the input and thrust and all the money behind it, unless there is passion, nothing is possible, because you need to keep driving, and passion ultimately drives, because that's when you lose count of time and day or whatever, and then you say, yeah, I see a problem I can solve with this. There's
another kind of passion too. Besides the personal passion, there's corporate passion, and a good example of that is the IBM. In that link I put in earlier, besides Terry Rudolph's book, there's another book available. It's called the IBM, the Quantum Decade by IBM. If you've never seen it, get that book. They're giving it out at conferences, and it's magisterial. It's like coffee table quality. They must have spent a fortune producing this book. You can just, when you make sure you download that one too. It's amazing. Anyway, why would they go through all this trouble and commit themselves publicly? They're giving it away, you know, not just online, but anytime you go to any conference now, IBM is at, there's a huge stack of them. And you know, normally that book will cost like $100, $150 if you bought it physically. It's gorgeous. So why would they go through all that trouble and commit themselves corporate wise to say this is the quantum decade if they weren't, you know, confident that in 2-3 years from now we're going to have some kind of, you know, commercial breakthrough? I'm just trying to support what you're saying.
Absolutely.
I think when I come to these conferences or here, you know, I mean, I think the question of money doesn't even arrive, because for me personally, I'm going to put a philosophical twist to it. And that is that, you know, no matter what money you have, you're not going to take it with you. But every experience, every passion that you nurtured, you're going to take it with you right the time you're leaving the world. And so what really matters is at that point in time is how many passions and how many things you really enjoy doing. Of course, money gives you a lot of freedom and, you know, but money doesn't come into this play for me anyway. And I think that's what I just wanted to point out.
I think you might have missed my point. I was trying to, everything you said, of course, is true. What I'm trying to say is, why would they risk their corporate reputation? You know, IBM stock, you know, 2/3 of that value isn't what they own. It's what their reputation, what people believe in the brand. So they're actually putting their money where their mouth is. That's my point. And risking their corporate reputation, which is worth billions on this quantum decade. I'm making this declaration that we're going to do quantum and it's here to stay. That's essentially what that book tells you. Thanks.
I mean, it is a real thing. Quantum is a real thing. So, you know, we're quite fortunate in the sense that this is becoming reality, and, you know, all these companies are investing that money, and all we have to do is connect it via the cloud, and we got it. We can actually experiment with some of the stuff, and that is the wonderful side of things.
First thing was Intel and all the progress they made with their Moore's law, and then they started getting those challenges, and then there were other players who came up in the field, and then cloud made things so much possible. And till we get all those expensive computers commercially viable, absolutely these simulators and everything through the cloud is making every piece of it possible. At least we're able to run through all these examples and everything what we say here. And if you remember, we started in AI also with an ELIZA program, and where we are today. I was seeing a very interesting example of, I mean, we all go to Starbucks. I am very sure if we are in the continent here, we all have visited Starbucks. If anyone has not, definitely raise your hand. I will not find anyone, definitely. And I was seeing how, and this is all something they realized before pandemic. There was a complete rollout of their concept in terms of digitizing their orders, in terms of mobile application, and in terms of picking up all in terms of which demographics, which geography you are coming from into the store. What is the temperature today? What is the time of traffic? How all this is happening, and how they are monetizing everything of you, your habits, your liking, and everything around you. And if you want to hear more about that, absolutely try to look at simple search of Deep Brew. And we know there has been a very recent transition back to Mr. Howard Schultz from Kevin Johnson, who's retiring. In fact, 4th of April, he did retire, and 5 years, but Deep Brew was mainly his baby, and how he basically came up with that idea. And all this was available to him as a concept before pandemic, which was realized in the stores. So when you could order, you were picking up at the end of the day, a common customer was thinking they are just picking up a cup of coffee using the phone app on Apple, or whatever smartphone you were carrying, and you were collecting some rewards, but you were providing plentiful data back to Starbucks as a company, where they were churning your data, they were utilizing your data, they were making you recommendations, doing all that predictive modeling behind the scenes. And when you were entering the store, sometimes they were even prompting you, hey, it's Christmas time, or hey, it's Halloween time. Would you like to try pumpkin latte? It's available now. Because sometimes you are so engrossed, you come into the store or wherever you are trying to order it from, you just think, I want my caramel macchiato. I don't care for anything else. But they were trying to basically, on the basis of what you were using, or if something you ordered last year, or they were even, I mean, we know, all of us, a lot of business happens in Starbucks. People come, sit over a cup of coffee, they meet. So they were even tracking, are you coming alone, or you are paying for 3 people's coffee, or you're paying for 5 people's coffee? Because there is something which they were struggling after, now they are struggling after the pandemic to deal with, that is third space. Your home, your work, the third spaces where you are picking up this coffee. And Starbucks was earlier known as what? The experience, whatever you are picking up, all those parameters, all that has been captured, and they're making use of all those parameters. As I was trying to reverse engineer this concept, what all has gone in, what all is being done in the background. You are talking on phone, there are 4 screens inside in the store, and those 4 screens are basically, one screen is only telling what is the digital order coming, one screen is taking speech to text, one screen is taking whatever is being captured in the store, and then the shift manager is there who's covering all these 4 screens and trying to manage and juggle the number of baristas. This is very fascinating example, but imagine if you were to go beyond these parameters and go even more, what is going to help? That's where even AI ML limitation will come, and that's where quantum is going to solve these problems. I rest my case.
Quantum machine learning definitely is a field that is taking off, and it seems to be amenable to some of the early hardware that is coming out. And of course, the hardware race itself is very exciting. It's by no means given yet what hardware is going to be the dominant one in 5 years' time, 10 years' time. At any rate, I unfortunately have a hard stop coming up, so I will have to excuse myself, but we can keep this call obviously open. But it's basically one last call from my end as a moderator here, officially moderating for any additional questions specifically to quantum teleportation. While we have the expert here still on site, because then 5:30 I unfortunately have to drop off. So anybody else? Yeah.
There is one thing I'd like to say on that, is that one of the problems with quantum computing at the moment is to do with error correction. And quantum machine learning, and starting with the machine learning itself, neural network, are going to play a major role in defeating that problem itself. So, you know, I mean, it is already being used widely to solve this very problem. And going forward, you know, I mean, there's a project that I don't I don't know if I should, I don't want to reveal it here. With something like a quantum machine learning and quantum computer, one can build a future machine, a machine that can predict future. In fact, predict your investments, since the talk is about money and things like that. Just taking a sidetrack.
No, that's very rightly said. You are very right there. And there are programs which are existent in the market. Chicago Computing is one such program. They were selling, and we had heard and we had talked to them. And at that time, as exactly you said earlier, they had the passion. They came out with a program which could take your small portfolio at a very meager cost of $50. They were making the prediction for you, forecast for you, basically predicting if your portfolio need to be balanced. But then that has exactly so much dynamic number of attributes to handle. And well, who would have expected a month and a half back that we will be seeing Russia-Ukraine war, and that will last in these times for more than 45 days. And that's something changing completely geopolitical scenario. What all we are going to see, there's a lot of extrapolation people are doing now, but a lot of things which we will see, they will unfold in the coming quarters or months or years, but that's something very interesting to watch.
Yeah, that's the quantum Monte Carlo, basically, is doing the so it's quantum optimization, which is doing, so you'll get financial stock portfolio optimization is done with classical Monte Carlo at the moment. So certainly, quantum Monte Carlo is a big game changer. Sorry, Henning, were you going to say something?
Yeah, it's essentially Monte Carlo simulation is one example, but you can essentially take any of the classical AI concepts and get them basically over onto a quantum platform. So one of my specialties is Bayesian networks, which is related to Monte Carlo simulations, where later you have a Markov chain, typically undirected probabilistic network. Bayesian networks are directed. And you can create quantum Bayesian networks, which essentially just handle quantum probabilities in addition to classical ones. And you can actually show mathematically that these structures are isomorphic to the density matrix. So any quantum system or any mixed system, you can actually model as these kind of networks. And then you can use the kind of training methods that have been developed for classical Bayesian networks to train these quantum Bayesian networks as well. And then, of course, we've seen the whole deep learning architecture being ported over to NISQ architecture. And the only costly aspect here is that you can't really do true backpropagation. You have to do it by forward propagation and then estimating the gradient and then do backprop that way. But essentially all concepts, classical machine learning concepts at this point that I'm aware of have been tried out and ported over to early quantum hardware. And they're all very promising in different aspects. The deep learning has been really fruitful in quantum chemistry simulations. But then again, I mean, it's early days, and any machine learning system in the end is but a high dimensional approximator. I mean, you're just basically creating a good approximation for the data that you're feeding it in. And in the end, if you get real life events that no data could possibly capture that you trained it with, and then all bets are off, right? I mean, nobody could have seen a thing like an external factor, like a invasion of Ukraine that nobody believed in. Nobody could put that into the training data, and then obviously no quantum computer is going to help you predict these kind of events. So there's always limitations that we have to be aware of.
Yeah, I mean, very rightly stated, very rightly said. As you said, training models and the future data for Ukraine kind of situation is not there. But the beauty, what you very rightly and nicely mentioned, is exactly in terms of all these deep learning algorithms and modeling and all these techniques. And if we go back, we had all these models basically worked out with very minimal levels. And we know when in the starting neural networks came into existence, we had theoretical existence, because after 2-3 levels, and when the things were going into recursion, things would bomb and in those situations. And then finally we got all the components and bells and whistles, and now we are going beyond so much. But then obviously whatever we have learned earlier, we have made use of it now. Whatever we are making use of all the classical AI machine learning stuff, we are now pouring it onto quantum. And obviously, if I say we have training models available in our machine learning situation, and they are giving rise faster to our predictions and our production models. They could become a very good training models for quantum in future. And that's why this transition, which we have taken 20 years, will be faster, and we could be able to basically achieve that faster. It will not wait 20 years, it will be much sooner because we have the right foundation and we have the right inputs there.
Absolutely. Yeah. On that note, I will have to sign off now. But thank you so much for this wonderful presentation and for the very lively discussion afterwards. And I'm looking forward to seeing you in the future on future Zoom calls like this.
Absolutely.
Helen, do you have the announcements? We didn't go over the announcements. You can do the announcements.
Can you see my screen?
Yes.
I can see your screen.
Okay, so the next event will be April 16th with John Barr and Dr. Solano. And the next one is May 1st on Sunday with Sadet and Neha. May 7th with John Barr and Nado. May 21st with Bombard and Pavel Gora. And May 25th with Dr. Barry Bird. And please follow Eamonn's Quantum Education Center of West Australia on Facebook. And also Powell will host another event with reinforcement learning for quantum technology. It will be happening on April 11th. And thank you, our sponsor for Quantum AI Foundation, Associate Quantum, ORX.net, and QBNet from Henning. Thank you.
Thank you all. We'll sign off.
Yeah, thank you.
Thank you.